In this short video, we'll look at system response. We're going to basically look at first order systems and second order systems. The reason why looking at first order and second order systems is because any system, any higher order system, can be written as a composition of a first order and second order system. The order refers to the highest uh, power of S in the Laplace transform of the differential equation. So we'll look at transfer functions and terminology. We'll look at what DC gain is. We'll look at a canonical first order system and its step response. And we'll look at a canonical second order system and its step response. Now, transfer function. The transfer function is the rational function solved by finding the output over the input in the Laplace domain. It is obtained by taking the Laplace transform of the differential equation and setting all initial conditions to 0. You've seen this before, but let's look at an example. Now you have a differential equation here, y double dot plus 3y dot plus 7y equal to u dot plus 4u. If you take the Laplace transform with 0 initial conditions of the whole equation, both left hand side and right hand side, this is what you get: y of s, capital Y of s times s squared plus 3s plus 7 equal to u of s times s plus 4. So y of s divided by u of s is s plus 4 divided by s squared plus 3s plus 7. This is the transfer function. Now note that the transfer function is independent of the type of input. You could have any generic input. This is basically a characteristic of the dynamic system. Let's look at a few transfer function properties. Now, transfer functions are defined only for linear time invariant systems. We know what linear systems are. So this here is a linear system. X dot equal to ax plus b u. U is a function of t. X is the variable of interest, which is a function of t. Now these constants a and b are not functions of time. Therefore, it is linear time invariant. On the other hand, if a and b are functions of time, then it becomes a linear time variant system. Transfer functions are independent of specific inputs. Transfer functions are the characteristic of a system. The roots of the numerator are the zeros of the system. Roots of the denominator are poles. So you can write the output divided by the input in the Laplace domain as a transfer function. The transfer function is a rational fraction, so you can write it as a numerator divided by the denominator. If you set the numerator equal to 0 and solve for s, you get the zeros of the system. You set the denominator equal to 0 and solve for s, you get the poles of the system. So the denominator set to 0 is the characteristic equation of the system. In other words, C of s, typically we write characteristic equation as C of s, which is equal to the denominator of the transfer function. If you set it to 0, it becomes a characteristic equation. Characteristic equation is very important. Everything depends on the characteristic equation. The characteristic equation tells you what the partial fraction expansion of y of s is. In return, it tells you what is the type of response, whether it's exponential oscillating, stable, unstable, etc. So it pretty much determines everything. So it's very important to understand characteristic equation. The transfer function is the Laplace transform of a system's impulse response. What does that mean? So let's say your input is an impulse function, and we know that the Laplace transform of an impulse function is 1. So if we write an equation for y of s as y of s equal to g of s times u of s, that's right from here, cross multiply like so, and set now for impulse u of s equal to 1. Therefore the output or the response is equal to the transfer function. So the transfer function is the Laplace transform of a system's impulse response. In fact, a lot of transfer functions in industry are found in this way. They just have a sensor at the output, and at the input they give an impulse like a hammer strike, get the time domain signal, and do a Laplace transform of that to get the transfer function. The differential equation can be obtained from the transfer function by replacing x of s by x, s times x of s by x dot, s squared x of s by x double dot, and so on and so forth. Now, other very important thing is to visualize the poles and zeros of the system, and for that we'll plot these poles and zeros, which in general are complex numbers, in the complex plane. So let's look at transfer function g of s equal to s plus 2 divided by s plus 1 times s squared plus 4s plus 8. So this is the numerator, this is the denominator. It has 1, 0 and 3 poles. Now if you look at this term here, if you do b square minus 4ac, you'll find that that's less than 0. So this is a complex pole pair, and if we complete the square and write it, this is what we get. Okay, this is the complex plane. So you have the y-axis, which is the imaginary axis, and the x-axis, which is the real axis. This is 0. This region here is the right half plane. This region here is the left half plane. Now let's plot the poles and zeros. The 0 is usually represented by a circle. Now I've just plotted the 0 at s equal to minus 2. How do I get minus 2? I set the numerator equal to 0 and solve for s. So s equal to minus 2. So that's excuse me, that's my 0. Then I have a real pole at s equal to minus 1. Poles are represented by crosses. And then finally I have my complex pair. If I set this equal to 0, I get s equal to minus 2 plus or minus 2i. And that's there right here. Notice that complex pair poles always come in pairs. You can't just have a single complex pole. Because of this, the pole zero diagram, this is called the pole zero diagram of any system, is always going to be symmetric about the real axis, always. Now let's do an example of finding the differential equation from the transfer function. As I said before, how do you do this? You replace x of s by x of t, s times x of s by x dot of t, s squared x of s by x double dot of t, so on and so forth. Now let's look at an example here. So y of s divided by u of s is s squared plus 2 divided by s cubed plus 2 s squared plus s plus 1. We'll cross multiply like so, and then we'll write it out. We multiply throughout, so you get s cubed y of s plus 2 s squared y of s plus s times y of s plus y of s equal to s squared u of s plus 2 u of s. So you replace this by y triple dot of t, this by y double dot of t, this by y dot of t, this by y of t, this by u double dot of t, and this by u of t. And that's your differential equation that generated this transfer function. Now, initial value theorem and final value theorem. These concepts are very important to understand the DC gain of a system. The initial value theorem states that the limit as t tends to 0 of a time domain function f of t is equal to the limit as s tends to infinity of s times capital F of s, where capital F of s is the Laplace transform of f of t, as long as this limit exists. The final value theorem is most important as far as we are concerned. A limit as t tends to infinity f of t is equal to limit s tends to 0 of s capital F of s. So essentially what it tells you is the final value of a time domain function is equal to the limit as s tends to 0 s times capital F of s. Now you have to be very careful when you apply this. This limit exists only as long as capital F of s is stable, i.e. as long as all the poles of capital F of s are in the left half of the complex plane.